Hi, today I'm going to talk about a very interesting problem related to RSA and AES. Let's get straight into the problem now. Bob has an RSA 2048 public and private key. We all know that that's good. So far, RSA 2048 has not been broken. So that's a good choice by Bob. He published his public key to the world. Of course, that's the meaning of public key. And for this problem, we assume that the public key is vetted by a certificate authority. So we can trust the public key is actually the public key of Bob. Okay, that's the basic facts about the RSA. And the next part is Bob wants to store some confidential file in his public cloud service. Okay, he has some public cloud service. Okay, storage service. So he wants to do it in an interesting way. He decided to use AES in GCM mode as follows. Since RSA 2048 private key is securely stored on a key store, for example, not in the cloud storage, but locally, he stored somewhere securely. And AES also needs a key, so he decided to use a simple trick. This is the important fact. He is now deriving a new key, which he calls AES key, by taking the RSA private key, the first 32 bytes of RSA private key, 32 into 8 is 256 bits, right? So AES, he is trying to use it with 256 bit key size, which is also great, because we know that AES is also not broken and doesn't leak information about the keys. So he thought instead of generating another AES key, he would take the RSA private key and just take the first 256 bits to derive the AES key. I think his reasoning is reasonably okay. There is nothing completely off because we assume the AES works good, RSA works good. There is no problem, right? Okay, so then he went ahead to the next step. He generated a unique random IV like this. He will basically call a random number generator and get an IV. He encrypts his file locally first before uploading to the server. You know, at this point, just assume there's an encrypt function that takes the AES key, IV, and the file, okay, and returns a ciphertext, okay. And the final step is that he uploads his IV and the ciphertext to the public cloud storage service. So the cloud storage provider would not be able to decrypt it because the RSA private key is not there, nor the AES key. So that's what Bob thought is, he's fine with this approach. So whenever he needs to decrypt, he will simply download the IV and the ciphertext from the public cloud storage provider. And of course, you need an AES key, so he will repeat the step number one. He has his RSA private key. He will take the first 32 bytes of it to produce an AES key. So, and then he will call the decrypt function, which will happily give him back the file. Okay, whenever he needs to modify his files, he will generate a new IV, encrypt the file using the AES key that he already generated, and he will repeat the steps 2, 3, 4. Okay. So step 1 is fixed, right? He got the AES key from RSA private key. That's the trick he did. Okay. So think about this problem. There isn't any easy vulnerability that will appear to you unless you are very familiar with fine-grained details of cryptography and your formal education in computer science and mathematics. Okay. Yeah, usually such a construction looks harmless, right? Because one number, RSA 2048 private key itself is a random number. And you are deriving another random number. In this case, is basically the chopping of the first 32 bytes of RSA private key and treat that as the AES key. It looks reasonably okay at the highest level when you reason about it. But the problem is asking, can E break this approach? This sounds like a scary problem. Okay, you have to break RSA or break AES, right? Because there's nothing wrong with Bob? Bob is doing perfectly fine because he's using RSA, he's using AES. Seems to be reasonable. So why are they asking us to think about this question? Can Eve break this approach? So let's go down further. Eve knows the public key of Bob. After all, Bob has a public key. So we have to assume the RSA public parameters like the public modulus n and E are public. And Eve also captured the ciphertext that was uploaded by Bob to the cloud service. So ciphertext is of course public. There's nothing confidential in the ciphertext. IV is also captured because it's also public clear text. So IV and ciphertext are clear text naturally. N and E are known from the public key of Bob. So the question now is, can Eve break this approach? Break in this case means, can Eve reverse engineer the plain text from the ciphertext? Remember, this is AES 256-bit key strength. The question is, can we take N, E, C, and IV as inputs and come up with the plain text that is hiding inside the ciphertext? This is a very interesting problem. I encourage you to think about it. Pause the video now and think about where can you find a way to break it. The approach requires some thinking, of course. The first step is to think about the key generation part. Well, Bob seems to be using proper RSA, so that's not the approach I would pursue. However, the step one seems to be something interesting to think about. He's taking the first 32 bytes of RSA private key, which is also private, so nobody can guess all the 32 first bytes of RSA. It may come across like that, but that's where the key is. So the rest seems to be everything perfect, right? He generates unique random IV, encrypts the file, uploads it. So there's not much hope here, in my opinion. So the only hope is to think about this part. All right, so in fact, there is a fundamental problem with this approach. The very act of just taking the first 32 bytes of RSA private key is dangerous. And I'm going to show you how to break the whole thing in a moment. Let's think about this. I have the slides from my public SlideShare website. And I'm going to select a few slides that are interesting or relevant for this particular problem, and then explain a solution how to break this. Okay. So we need to quickly recall how RSA works. So I will go to the RSA algorithm slide very quickly. There's a lot of value in understanding how RSA actually works. Otherwise, you wouldn't be able to break this kind of problems. Okay. So consider this. There are a few mathematical notations I will briefly explain. What is the key step? Okay. If you are using RSA key generation algorithm, first thing you would do is you will select the desired key strength, for example, 2048-bit or 4096-bit and so on. So you will select that. And RSA will generate, the key generation algorithm will pick two independent large random prime numbers, P and Q. Okay. And then those two numbers are multiplied to form another number called n, which is the public modulus. All right. And then it goes ahead and computes something called pi of n, which is the Euler's torsion function. Pi of n is basically made of couple of things. Pi of n denotes, by the way, how many numbers are relatively prime to n. Okay, less than n, but relatively prime to n. That's the measure of pi of n. So if n is a composite number, pi of n is easy to compute. It's nothing but p minus 1 and q minus 1. Okay. All right. And now comes the public exponent and the private exponent part. In RSA, the public exponent is E, which is usually a fixed constant. D is the private exponent, which is of course private. No one should know it, otherwise they will break the whole system. How is D constructed? D is constructed from E and pi of n. Okay, pi of n itself is difficult to compute if you don't know P and Q, which is true in RSA case. Only the key generator will know the P and Q. So from equation number 5, D is derived based on the knowledge of E and pi of n. But there is an interesting problem here. Pi of n itself is not easy to calculate. But we can try to think of how close pi of n is to the number n, for example. And the idea is to approximate pi of n by n and see whether we can guess a private exponent d which is reasonably close to the original exponent. Okay, for our purpose, reasonably close means can we guess the first 32 bytes of the private exponent d correctly? That's all we are trying to do. Instead of guessing all the 48 bits, we are trying to guess only the first 256 bits. Okay, since the problem is asking us to use AES in 256 bit. Okay, so let's recap now. E is a constant. It's usually 65,537, something like that. Pi of n is not known, but still we can approximate pi of n by n because n is public, and therefore we can approximate d by something closer to this d, and thus we can derive the first half of d actually. Not only just 256 bits, but we can derive the first 1024 bits of d. That's amazing. So to sum up, we have n and e public. We have pi of n d p q as private. That's the summary. So now let's look at how do we approximate the unknown d and guess a reasonably good d. Okay. All right. So I will skip some of the slides. That's not important at this point. Okay. So if you recall the previous equation, I said E dot D is congruent to 1 mod pi of n. Right. That's what I said earlier. Something like this. E dot D is congruent to 1 mod pi of n. Okay. What does this mean really in terms of mathematical equation? It really means E times D minus 1 is a multiple of some constant times pi of n. That's the meaning of this particular expression, right? So it turned out that if E times D minus 1 is equal to K times pi of n, K has to be less than E. Okay, that's the mathematical fact, and I'm not going to give you a proof for that. So I also mentioned that E can only be up at most 65,537. You can still choose large E if you want, but that's not the way it works in practice. Most implementations stick to the default E value. Okay. So what is the point of this slide? This slide is just telling you that E times D minus 1 is multiple of K times pi of n. K must be less than E. All right. So what is the approximation algorithm? So this is this beautiful paper written by Professor Dan Bonnet, and he talked about how do we approximate the private exponent by another private exponent, and I'm going to talk about that, skipping some of the details of the proofs because it may not be interesting for you at this point. Okay, so how do we handle it? Here is the trick of the trade. So we do know E times D is congruent to 1 mod pi of n, but pi of n is nothing but p minus 1 times q minus 1. Again, we don't know p and the q. Only the person who owns the private key knows p and the q. Okay. We also don't know k either. We do know it must be some multiple of k. So if you apply some basic algebra now, it becomes pq minus p minus q plus 1. This is just coming straight from the basic arithmetic. And then if you just reorder the terms, your d is nothing but 1 plus k times n minus p minus q plus 1 by e. Okay. But now we still have a bunch of problems. We don't know k, we don't know p, q. But that's okay. The reason why that's okay is this. Recall the fact that p and the q are the size of or half of the size of n. If n is a 48-bit number, both p and the q are 1024-bit numbers. So that's an important fact. P and the q are just half of the size of n. Okay, that's important. Why is important? Because think of the value for n minus p minus q. If n is a 48-bit number, p and the q, if you add them together, it will be only 1024-bit number. So you have a situation like this. You are subtracting n, which is a 48-bit number, for example, right? Again with another 1024-bit number. Okay. because when you add 2024-bit numbers, there may be a carry bit, but anyway, it may be at most 1025. That doesn't matter. So what is the point of this? Now, if you subtract a 2040-bit number with another 1024-bit number, subtraction doesn't change the size. So you will get, as a result, another number which is still 2048-bit number only, right? So this factor n minus p minus q plus 1 times some k is usually about 2048-bit. All right. So what does that mean? That means that if we replace now by instead of using this n minus p minus q plus 1, because we don't know p and the q, we just replace it by k times n. We just ignore p and the q and 1. Okay, that's what we are doing. So we ignore the p and the q, and we get an approximation like this, right? 1 plus k times n by e. And now, what are the things we know? We know 1, of course, it's a constant. We know n, we know e, but we don't know k. All right. We do know learned that k must be bounded by e. So we can just try k to be 1, k to be 2, all the way up to k to be e, right? At most, that's what we learned in the previous proof. So all we have to do now is just make a guess. Start our private key to be starting with the value k equal to 1, k equal to 2, k equal to 3, and so on. We're going to try at most 65,000 attempts approximately. And for each guess, we will decrypt the ciphertext. If the ciphertext reads reasonably okay, we know that our guess is correct. Therefore, we have broken the scheme. That's the idea. Okay, so to sum up, what we are seeing here is that we have an approximation of the D by another approximation called D cap, right? Basically, we replaced P and the Q, and we ignored it because subtracting a 2040-bit number from a 1024-bit number, it will give you back a 2040-bit number anyways. So why not just leave the P and the Q and make that as an approximation? That's the idea. Okay, so I implemented this. Now I can go back to the code. The code takes the RSA public model as n, e, and then the ciphertext IV. These are the 4 arguments we already got from our problem statement. If you recall the problem statement, we got the RSA public value n and e, the ciphertext, and the IV. Now we can first let's run it, and then I'll show you the solution. Okay, I already created the environment variable n, e, c, and IV based on the problem statement, so we can just quickly run it. So when our k is 49,420, we got a text that is readable and it looks reasonable good. You see here, random is a tricky concept, not easy even for people with formal CS math background. Avoid deriving keys in an ad-hoc fashion. That's the message that has been encoded in this ciphertext. The ciphertext that we got has that data. Okay, it's AES encrypted, everything is perfect. But there's a fundamental problem in the key derivation. So he took the first 32 bytes of RSA private key to construct the AES key. He was thinking that, of course, nobody can predict all the 256 bits. That's the reason he was thinking like this. But he was fundamentally wrong. Bob was fundamentally wrong. There isn't much entropy. Entropy means uncertainty in RSA for the first half of the private keys. In fact, you can predict all the 1024 bits of the 2048-bit RSA private key. The first 1024 bits, the most significant bits, are available for free, more or less. You have to try just 65,000 attempts to know the possible values. Okay, now I will explain the algorithm a little bit, what I did. I think you already saw the algorithm on the slides, but I will quickly walk through the code, how it works. It may not be the best structured code, but it's okay for our purpose. We have n, the public modulus, the RSA public exponent, and the AES ciphertext and IV, 4 inputs, right? What we are doing is we start guessing, right? We say guess the private exponent. The guess algorithm is simple. Let me show you how the guess algorithm works. It guesses the k value to be 1, and then computes 1 plus k by n, k times n by e. That's the thing that I shown on the slide. And then it runs in a loop, so it returns all possible guesses, right, in an array. And then once the guess is done, the algorithm, what it does is it takes each guess, takes the first 256 bits, right? That's what we need. So you see here, it takes the integer that is coming from the guess and just uses the AES key size, which is in this case 256 divided by 8 is 32 bytes. So it takes 32 bytes of the guessed private exponent, right? And then it makes a decryption call. If the decryptor returns something gibberish, usually it's not printable, then is ASCII printable is a little utility I got from the internet. It checks whether all the characters are ASCII characters are printable, no funny looking characters. If that's true, it prints the plain text, and it'll continue because there may be occasionally some plain text that are printable, but very, very rarely that you would see anything. Like I tried it now without even a break statement, right? So it was trying 65,000 times, right? And only one of the output has some meaningful English text to be printed. Okay. Anyway, so the point I was trying to tell you is that there isn't any uncertainty regarding the first n by 2 bits of an RSA key. Okay, that's more or less available. So you should not be just taking a large number and just taking the first half of it or the first 256 bits and so on. That's completely dangerous.